Welcome to our deep dive into enterprise AI system design. In this video, we'll explore the architecture and practical strategies behind retrieval augmented generation, RAG, agentic workflows, and robust system integration. Whether you're an aspiring architect or a business leader, understanding these concepts is crucial for building scalable, efficient, and secure AI solutions. We'll walk through real-world examples, best practices, and common pitfalls, ensuring you gain a comprehensive view of modern AI system design. Let's begin by setting the stage with the foundational elements of end-to-end architecture. An enterprise RAG system is typically divided into two main pipelines, the ingestion pipeline and the retrieval generation pipeline. The ingestion pipeline handles document sources, extracting and parsing text, chunking content, embedding it, and storing it in a vector database. Retrieval generation pipeline starts with a user query, reformulates it, performs vector and hybrid keyword searches, re-ranks results, compiles prompts, injects context into the LLM, checks guardrails, and finally streams the response. This dual pipeline approach ensures both accuracy and efficiency in enterprise environments. Ingestion pipeline is the backbone of any RAG system. It begins with collecting documents from various sources, which are then converted into text. This text undergoes extraction and parsing to ensure only relevant information is processed. Next, a chunking strategy splits the text into manageable pieces, which are then transformed into vector embeddings. These embeddings are stored in a vector database, ready for efficient retrieval. This process is crucial for maintaining up-to-date and searchable knowledge bases in enterprise applications. When a user submits a query, the retrieval and generation pipeline springs into action. The query is first reformulated for clarity, then sent through both vector and hybrid keyword searches. Results are re-ranked for relevance, and the most pertinent chunks are compiled into prompts. These prompts are injected into the LLM context, guardrails are checked for safety, and the final response is delivered, often in a streaming fashion. This pipeline ensures users receive accurate and contextually relevant answers. Imagine an AI agent capable of coding, testing, and debugging itself. This system is designed as a three-node cyclic graph. The coder node writes code based on instructions and commits it to a sandboxed environment. The tester node executes the code in a secure Docker container, capturing outputs and errors. If errors occur, the debugger node analyzes logs, reasons through fixes, updates the code, and routes execution back to the coder node. This cycle continues until the code runs successfully, enabling autonomous development. For an e-commerce platform, an AI customer support bot must efficiently route user requests. At the entry point, an intent classifier agent determines the nature of the request. Order status and refunds are routed to a deterministic agent with database access. Product inquiries go to a semantic search RAG agent over product catalogs. Chit-chat and complaints are handled by an empathetic dialogue model with strict context guardrail. This architecture ensures users receive accurate and contextually appropriate support. Legal documents are often long and highly structured, requiring a specialized chunking strategy. Recursive character chunking combined with hierarchical or parent-child chunking is ideal. This approach respects document headings and sections, ensuring that context is preserved. Parent-child chunking indexes small subchunks for precise retrieval, but returns the entire parent section to the LLM for complete context. This method balances retrieval accuracy with context preservation, which is critical for legal and compliance use cases. Rankers such as Cohere Rank or BGE Ranker play a vital role in production RAG systems. While vector search is fast, it often lacks deep context understanding. Rankers use cross-encoders to evaluate the semantic relationship between queries and retrieved chunks, narrowing down results for higher accuracy. For example, pulling the top 50 documents via vector search and re-ranking to the top 5 ensures precise answers with minimal latency. This step is essential for enterprise-grade retrieval quality. Handling multimodal inputs such as images and text is increasingly important in automation, especially for insurance claims. The system routes raw input fields to a multimodal LLM like GPT-4o. Text describing the incident and photos of the damage are processed together. Text is extracted via OCR or vision parsing, structured into JSON, and matched against policy documents using RAG. The system then outputs an initial validation assessment, streamlining the claims process. Managing session state and historical storage is crucial in multi-tenant AI systems. Active session states are maintained in a centralized caching database like Redis, tagged with a session ID. When a session ends, the chat transcript, summary embeddings, and metadata are persisted in a permanent document store, such as MongoDB, partitioned by tenant ID. This approach ensures both real-time performance and strict data isolation across clients. Allowing AI agents to execute arbitrary Python code introduces security risks, such as malicious commands or resource exploitation. To mitigate these risks, code execution must occur in ephemeral, sandboxed environments like isolated Docker containers. These containers should have restricted network access, CPU limits, read-only file systems, and short time-to-live settings. Such isolation ensures that even if malicious code is run, it cannot affect the broader system. Documents change frequently. Keeping the vector database up to date without downtime is a challenge. An asynchronous event-driven architecture solves this. Document management systems trigger webhooks which send events to a message queue. A worker pool then processes these events, chunks documents, generates embeddings, and updates the vector database in the background. This ensures live queries are never interrupted, maintaining high system availability. Query expansion layer enhances RAG retrieval accuracy by generating alternative query variations. Before querying the vector database, an LLM creates 3-5 subqueries for vague user inputs. The system performs parallel vector lookups for all variants, aggregates the results, and applies reciprocal rank fusion to select the best context chunks. This approach captures more relevant information, especially for ambiguous or broad queries. For demonstrating a complex AI system to stakeholders, thorough evaluation is essential. Start with unit tests for core tools and custom logic. Next, run batch evaluations on benchmark test sets, using an LLM as a judge to assess reasoning and tool selection. Finally, conduct manual edge case testing, or red teaming, to verify security and guardrails under adversarial conditions. This multi-tiered validation ensures the system is robust and ready for production. Choosing between a graph database and a vector database depends on your retrieval needs. Vector databases excel at finding local, topical similarities within single documents, but struggle with connecting relationships across a broader ecosystem. GraphRag, on the other hand, maps entities and their connections, making it ideal for synthesizing global systemic queries. However, graph databases come with higher ingestion complexity and processing overhead. Automated data flywheel captures all production inputs and outputs, logging both implicit user signals and explicit actions. Low-score or downvoted samples are routed into an annotation pipeline for evaluation. These curated datasets are then used for prompt adjustment testing or model fine-tuning. This continuous loop ensures the AI product evolves and improves based on real-world usage and feedback. Long-running projects like corporate report generation can hit LLM rate limits. To address this, use an asynchronous batch job architecture with queue-based chunking. Split the workflow into subtasks, each managed by a task framework like Celery. Workers process tasks individually, monitoring token rates and applying adaptive sleeping if rate limits are reached. This ensures smooth, uninterrupted processing even for large-scale tasks. Hybrid search combines dense vector retrieval with sparse keyword search, such as BM25. This approach is preferred in corporate systems because pure semantic search often misses precise alphanumeric terms, serial codes, or proprietary product names. Hybrid search ensures both contextual understanding and exact term matching, making it highly effective for enterprise information retrieval. Porting low-power edge devices requires careful optimization. Techniques like model compilation, distillation, and aggressive quantization, e.g., INT4 or GGUF formats, help fit models into limited hardware. Specialized engine backends such as ONNX Runtime or TensorRT-LLM further enhance performance. Prioritizing compact local foundation models ensures efficient AI operation even in resource-constrained environments. Semantic deduplication is essential in high-volume data ingestion pipelines. As new data blocks are processed, hashes or high-density embeddings are calculated. A fast similarity search checks for matches with existing vector collections. If a new block closely matches an existing chunk, it's discarded or merged, saving index space and preventing duplicate context retrieval. This keeps the knowledge base clean and efficient. Ensuring data isolation across multiple enterprise clients is critical when using a single vector index. This is achieved through strict metadata filtering. Each vector node is tagged with an immutable identification field such as tenant ID. When querying, a metadata filter ensures only nodes matching the specified client are accessed, maintaining privacy and compliance. Determine if an agentic workflow delivers business value over traditional heuristics. Set up an A/B testing framework. Measure objective KPIs such as task resolution success rate, average user interaction duration, automation redirection rates, operational costs, and human agent takeover requests. This data-driven approach provides clear insights into the effectiveness of AI-driven automation. Presenting complex AI architectural failures to non-technical leadership requires clarity and relatable analogies. Avoid deep technical jargon. Instead, frame issues as trade-offs such as processing speed versus cost or accuracy risks as confidence metrics. Use data visualization dashboards to map product enhancements directly to business outcomes, making technical limitations understandable and actionable. Integrating all components into a cohesive system is a critical step in enterprise AI design. This involves aligning data pipelines, agent workflows, and security measures. Proper integration ensures seamless data flow, robust performance, and easy scalability. Regular testing and monitoring are essential to catch integration issues early and maintain system reliability. Guardrails are safety mechanisms that ensure AI systems operate within defined boundaries. They check for inappropriate content, enforce context limits, and prevent unsafe actions. Implementing robust guardrails is especially important in customer-facing or high-stakes environments, where errors can have significant consequences. Regularly updating and testing guardrails keeps the system secure and trustworthy. Prompt compilation is the process of assembling relevant context chunks into a coherent prompt for the LLM. This step is crucial for maximizing the quality of generated responses. Effective prompt compilation balances the need for context with token limits, ensuring the LLM receives all necessary information without exceeding capacity. Automation tools can streamline this process for large-scale systems. Streaming response delivery allows users to receive answers in real time as the LLM generates them. This enhances user experience, especially for long or complex queries. Implementing streaming requires careful management of data flow and error handling, but the result is a more responsive and interactive system. Docker containers are widely used to isolate code execution in AI systems. By restricting network access, limiting CPU and memory, and using read-only file systems, containers provide a secure environment for running untrusted code. Regularly updating container images and monitoring for vulnerabilities further strengthens security. Event-driven architectures are essential for building responsive and scalable AI systems. By using webhooks and message queues, systems can react to changes in real time, updating databases and triggering workflows without manual intervention. This approach is particularly effective for handling frequent document updates and asynchronous processing. Message queues such as RabbitMQ or AWS SQS are used to manage asynchronous tasks in AI systems. They decouple task submission from processing, allowing worker pools to handle jobs at their own pace. This ensures system stability and scalability, even under heavy workloads or during batch processing. Worker pools are groups of processes or threads that handle background tasks, such as document chunking or embedding generation. By distributing work across multiple workers, systems can process large volumes of data efficiently. Monitoring and scaling worker pools ensures optimal performance and resource utilization. Metadata filtering is a powerful technique for enforcing data isolation and access control. By tagging data with metadata fields such as tenant IDs or access levels, systems can ensure that only authorized queries retrieve the correct information. This is especially important in multi-tenant environments where privacy and compliance are paramount. Annotation pipelines are used to curate and label data for model improvement. Low-performing or ambiguous samples are routed to human annotators who provide feedback or corrections. This curated data is then used for prompt adjustment or model fine-tuning, creating a feedback loop that drives continuous improvement. Red teaming involves simulating adversarial attacks to test the security and robustness of AI systems. By intentionally probing for weaknesses, teams can identify vulnerabilities and improve guardrails before deployment. This proactive approach is essential for maintaining trust and reliability in production environments. Using an LLM as a judge in evaluation workflows allows for automated assessment of reasoning and tool selection. This approach provides consistent, scalable validation, especially when benchmarking complex AI systems. Combining LLM-based and manual evaluations ensures comprehensive coverage and high-quality results. Monitoring token rates is crucial for managing LLM rate limits. By tracking usage and applying adaptive sleeping policies, systems can avoid interruptions and maintain steady throughput. This is especially important in batch processing or long-running workflows where exceeding rate limits can disrupt operations. Compact foundation models such as Llama 3.8b or Phi-3 are designed for efficient deployment on edge devices. These models balance performance and resource usage, enabling AI capabilities in environments with limited hardware. Selecting the right model is key to achieving both speed and accuracy. Reciprocal rank fusion (RRF) is a technique for aggregating results from multiple query variants. By combining rankings, RRF selects the most relevant context chunks for the final response. This method improves retrieval accuracy, especially when dealing with ambiguous or multifaceted queries. Parent-child chunking indexes small subchunks for precise retrieval but returns the entire parent section for context. This strategy is especially useful for structured documents like legal texts, where maintaining context is as important as pinpointing specific information. It ensures both accuracy and completeness in retrieval. Hierarchical chunking respects the structure of documents such as sections and headings. By chunking at different levels, the system can retrieve information at the right granularity. This is particularly effective for long, structured documents, ensuring that both detailed and high-level context are available to the LLM. Hybrid keyword search combines the strengths of vector and keyword-based retrieval. While vectors capture semantic meaning, keyword search ensures precise matches for terms like serial numbers or product codes. This dual approach is essential for enterprise systems that require both accuracy and specificity. Isolating code execution in Docker containers protects the host system from malicious or faulty code. By configuring containers with strict resource limits and network restrictions, organizations can safely enable AI agents to execute code without risking broader system integrity. Redis is commonly used for centralized caching of active session states in AI systems. Its speed and scalability make it ideal for managing short-term data, such as ongoing conversations. Once sessions end, data is moved to permanent storage, ensuring both performance and persistence. MongoDB is often used for permanent storage of session transcripts, embeddings, and metadata. By partitioning data with tenant IDs, MongoDB ensures strict isolation and compliance. This combination of real-time caching and long-term storage supports both performance and data governance. Summary: designing enterprise AI systems involves careful planning across architecture, data pipelines, agent workflows, and security. By leveraging best practices like hybrid search, robust chunking, secure execution, and continuous evaluation, organizations can build scalable, reliable, and effective AI solutions. Remember, the key to success is balancing innovation with operational excellence, ensuring both technical and business goals are met.